The last section we are going to take a look at is 3.5. The plan is to put a list of topics at the end of the video that will be on the test tomorrow. So if we have enough time, I'll do it in class. If not, I'll finish it up after and I'll post it on YouTube. Okay, so the first thing we're going to do is we're not even going to get to, eventually we want to do problems like this, find the zeros. Just like the kind of problems we did yesterday. The thing that's going to happen here, though, is they're going to come out imaginary. So we're just going to review first what imaginary numbers are, and then we'll try some of those questions. Okay, so let's just review some of those names. If you have a number that you can plug into a function, and it gives you 0 as an answer, what do you call that? Yeah?
A root.
You call it a root, yep.
Or a 0.
Or a 0. And what does that mean if you graph it? It's an x-intercept, yes. So if you, let's say you could plug in the number 3, right? And it gave you 0. So we could have something like f of x equals x minus 3. So that's a very simple linear equation. If you plug in 3, you get 0. The x-intercept of that is 3, 0. That's where it would cross the x-axis. Now, what if a graph never crosses the x-axis? What if it looks like this? What would that mean? Yeah.
It has no zeros.
It has no certain type of zeros.
It has no real zeros.
It has no real zeros, right? So if a polynomial doesn't cross the x-axis, it's not, there's no solution. There's no real solution. So let's look at graphing y equals x squared plus 1. Right, so I'm going to type that in. So x squared plus 1. And that's a parabola. And does anyone remember when you put a plus 1 on the end? Which way does that shift it?
Left one.
Left one would be if it was like inside parentheses. That's going to shift it up 1 because it's on the end.
Yeah.
So zoom 6. Right. So if you look at that graph, does it ever cross the x-axis?
No.
Nope. Doesn't mean we can't set it equal to 0 and solve it. It just means if we did, we'd get imaginary answers. All right, so to solve that problem, we're going to end up using something called I. And I is up on the board. And I is defined to be the square root of -1. Now, there's no reason why that's true, or it's not something you can explain. It'd be like if you said to me to explain why parallel lines don't cross. I can't, because parallel lines not crossing is the definition of parallel lines. It's not something you can prove. This is kind of the same idea. I equals the square root of -1. That's just decide what they decided to call it. Because before that, they didn't have a symbol to represent it. Okay, so they used I. Now, what's going to happen when we do some multiplying is we're going to end up with I squared. Okay? And that we need to know how to simplify. Okay, so here's I. And there it is squared. What happens when you square and square root something? What happens? It cancels out. And you're left with what was under the root symbol to begin with. So what would you get if you take the square root of -1 and square it? You would get -1. So anytime that we have a problem and we end up with I squared, we have to make sure we always change I squared to -1. Any question on that? So I squared is always the number -1. let's try plugging in I into the equation we just graphed on the calculator, and let's see what happens. So plug in I for x. You get I squared plus 1. What did we just say I squared is? I is the square root of negative 1, but I squared negative 1. So that equals 0. When you plug in I, you get 0. What does that mean that I is?
0.
It's a 0. Yeah. I is a 0, or we could also say I is a root. Is I an x-intercept? No. That doesn't apply when you talk about imaginaries. It does when you talk about real. Any questions why I is a 0? Or a root? Yep.
Since x is being squared already, if you're plugging in, you're just plugging in. Never mind.
We're just plugging in I. So you're doing this.
Answer my own question.
So you end up with just negative 1. Okay, so I is an example of a symbol that we use when we have complex numbers. That is generally how you want to write a complex number. Real part comes first, then the imaginary part with an I. And here's some different examples. 3i and negative 7i. Those are what we call pure imaginary numbers, because 3i and negative 7i don't have a real part with them. I guess you could think of the real part as really being what number? 0. It's like 0 plus 3i. Okay, there's no imaginary, no real part. Okay, 4. Well, that's still considered a complex number, but the imaginary part would be what in the number 4? Yep.
0.
0. Yeah, 0i. There is no imaginary part in the number 4, so because it's 0, we normally don't even write it. We just write the number 4. Yep.
So is that with that one, it's number with 4, does that mean that there's always like an imaginary, a 0i next to every number, or is there specifically a 0i by that one?
There's a 0i next to every number.
Okay.
We just normally don't write it because when we're talking about real numbers, that's just a lot more stuff to write down, and it looks more confusing.
Okay.
But yeah.
So like if you had any answer to any math problem ever that didn't have imaginary numbers, you could put 0i next to it?
As long as, I can't think of an example where you can't.
Okay.
Unless the answer to the problem is something that's not a number.
Yeah.
Like, I don't know, like if you divide by 0, that's undefined, so that's a totally different situation.
Okay.
But yeah, in general, every single number falls under what we call complex numbers. That's the big category. Complex. Complex. Under complex, there's 2 branches. There's real, and then there's imaginary. Everything you do in Algebra 1 falls under the real part. When you get to Algebra 2, that's when you also start looking at the imaginary part. But every number that you've probably ever studied, and that I think I've ever studied, falls under complex. Sometimes the imaginary part, though, is a 0. Yeah.
If you're saying 0i, isn't it just saying that it's not imaginary?
Well, it's just saying that the imaginary part is 0. Yeah.
Oh, because you're multiplying by the square root of negative 1 by 0, so it just has to be 0. Okay.
So yeah, there is no imaginary part. Every number in Algebra 1 that you study is just real. There is no imaginary part to it. But it's still complex. Everything is complex. Everything's complex.
Is there non-complex numbers? Is that what groups are?
There might be, but I'm not really familiar with what they would be.
Are groups considered complex numbers, or
Groups?
yeah,
Like a group of numbers?
like the I forget the types, octonials.
I'm not sure.
Okay.
I'd have to read more about that. I don't know.
All right.
Yeah. But yeah, everything that we study is complex. Okay, so think of complex as just like the big umbrella. Here's another complex number. The real part is 2/5, and the imaginary part, if you don't ever see a number in front of I, you can always pretend like it's a 1. Okay. So any questions on the way that we write a complex number? Real part, then imaginary part. And those are all different examples. All right, so what we're going to do now, and then this will be the last part of the review, is we're going to do an add, subtract, a multiply, and a divide. We'll do one of each with complex numbers. So when you are adding or subtracting, you can think of I almost like it's x. Like if you had 3x plus 2x, what would that be? 5x. Well, if you have 3i plus 2i, what do you think that would be?
5i.
Yeah, it would be 5i. So we can kind of treat it the same way we would do combining like terms if it was an x or a y or anything else. When you multiply, you're going to have to end up using the double distributive property, which means you're going to get some I squareds in the problem. Anytime we get an I squared, we have to remember to change it to -1. When we do a division problem, we're going to do one of each. But when we do division, we don't actually do division. Okay, to divide complex numbers, you actually use multiplication. And specifically, we're going to multiply by something called the conjugate. So I'll show you what a conjugate is, and then I'll show you how to use it. Oh yes, square roots. So when you have a square root, you can't leave the negative under the square root. You have to fix this negative. And I'm going to show you how you fix it. What number is in front of this x, even though it's not written?
1.
Right, it's like a -1. It is like a -1 in front of that x. So does everyone agree that I could do something like that if I wanted to?
Mm-hmm.
Yeah, that's the same thing. I just put the -1 in front of the x. Now, when you multiply two things together under a square root, you can take the square root of each one of them separately. Just like if you had the square root of 4 times the square root of 9. You can break that up into square root 4 times square root 9. You can separate it into 2. So in this case, it would be 2 times 3, which gives you 6. Or if you think of it this way, 4 times 9 is 36, and the square root of 36 is 6. Well, let's try it here. So when I split it up, one of these we just talked about. It has a symbol to represent it. Which one of these can I simplify? Yep.
You can simplify the square root of -1 to I.
Right. The square root of -1 turns into an I. So the point, or what happens, every time you take the square root of a negative number, the negative comes out in the front as an I. That's what happens. Okay. The negative will just come out in the front as an I. Now, I know when I wrote the example earlier, I put the I at the end. I put the I after the imaginary part. Why do you think with a square root, I don't want to put the I, like if I had something like this? Why do you think I'm saying to put the I in front of the square root? Like that. Yep.
I have like two answers, but one of them it could be confused that's inside the square root.
Right. You could be confused that the I is in the square root, and it definitely should not be. So when I look at this first one, I can't really tell. Is it under it? Is it not under it? But when I look at the second one, the I is in front, so it's very clear that it's not under the square root. So the only time you put the I in the front is when you have a square root like that. Okay. Other than that, let's say you had like this, I square root of 4. Well, I would just say that that's 2i. Because the square root of 4 doesn't have to stay. You can get rid of the square root and just make it a 2. All right. So any question on when you should leave it before versus put it after? It's just a clarity thing, so it's easier to read. Yeah, did you have another?
Well, the other thing was just like, is it a problem if it's like square root of 3 and then you can see it as like times I?
I mean, I guess you could do like square root of 3 and then in parentheses times I. That's also very clear that the I is not under the square root.
Okay.
Just to save having to write 4 extra parentheses, they usually just put it in front. But that is clear. Yeah. Right. Let's try these two. The square root of negative 4, and then the square root of negative 7. So let's start with square root of negative 4. So think about what's going to happen to that negative. Well, kind of already did this problem right up above. Yeah.
2i.
It's 2i. Yeah. It's perfectly fine to put the I after the number because there's no root. The square root disappeared because it was a perfect square. How about the square root of negative 7? How would we write that one? Yeah.
I square root of 7.
Right. I square root 7. So the negative just comes out in front as an I. All right. How about this one? The square root of negative 9. Yeah.
I square root of 9.
Okay, so you could start with that,
Yeah, sorry.
and then you could simplify it to 3i. Yeah. Okay, and how about this one? Square root of negative 20. We might, well, I won't say anything yet. You tell me, and then we'll kind of go from what you say. Yep.
Would it be I square root of 20?
Okay, so you could start with I square root 20.
But you can simplify it.
Right. How can you break down the square root of 20? Two numbers that multiply to give me 20, but one of them I want to take the square root of. 4 times 5.
I2 square root 5.
Yep. And how would we normally write I2?
2i.
2i. Yep. Okay, so that's how you simplify square roots. That's going to come up when we do quadratic formula. We're going to end up with a square root. Going to be a negative under it sometimes. And then we have to simplify it just like we did here. Sometimes it'll simplify because you have a perfect square. Sometimes all you can do is break it down. Any questions on that? Okay, so now let's try and add, subtract, multiply, and divide. Okay, when you add complex numbers, you do not do distributive property. You would do distributive property in a problem like that. That's not adding, that's multiplying. That's adding. All you can do when you add them is combine like terms. So, like terms mean you can combine real numbers with real numbers and imaginary with imaginary. In this case, when I say combine, I mean add. Okay. So if you combine those together, what would be the real part when you add the two real parts you have right there? Yep, it's going to be 11.
And then 2i plus 2i.
And then a negative 3i plus 5i is 2i. Yep. Okay, so that's adding complex numbers. Right, subtracting, pretty similar, except think of this negative as being distributed. So you're going to subtract 6 from the real part in the first parenthesis, and then you're going to subtract I from the imaginary part. Right, so what's the real part going to be when you subtract these two? Yep. So it's going to be 4 and then minus the 6. And then negative 2i minus the I. Negative 3i. So just like adding, except you distribute the negative and then combine like terms. Any questions on adding or subtracting?
I think I'm ready for this testing right now.
Right now? You want to do it?
No.
I think it's
I'm good.
I think
All right, so multiply. Multiply, that's where you have to use 4. So we're going to go like this. Then we're going to go like that. All right, so let's start. Brady, what's 2 times 5?
10.
So that gives me 10. Okay, Ethan, what's 2 times negative I? It's just like you would do 2 times negative x. It'd be the same answer, except say I instead of x.
Okay, so negative 2i?
Negative 2i. Yep. Negative 2i. What about 5 times 3i? That's going to be 15i. Now let's take the last part in a couple steps. It's a positive times a negative. So what's a positive times a negative?
negative.
Okay, so it's going to be a negative. And it's 3i times I.
Negative 3 out to the second.
Negative 3i to the second.
So would that just be 30?
Okay, now what did we say? Well, actually, we can do a couple things. What's negative 2i plus 15i? So it's 13i. And now, what did we say about I squared?
It's negative 1.
I squared is negative 1.
So it's just positive.
So that's going to become, instead of a minus 3i squared, that's plus 3. And then once you change it to a plus 3, you can combine it with the other real part. So what's going to be final answer?
13 plus 13.
Yeah, it's just a coincidence they're both 13s. That usually doesn't happen. 13 plus 13i. Okay, we are going to do another multiplication when we do division, but any questions on that? All right. So, division. Well, in order to do division, what ends up happening is that here's a problem. Let me find one. Okay, this is the one we're going to do in a minute. You can't leave I in the bottom. It's kind of like you can't leave a square root in the bottom. You can't leave the I in the bottom. So we just need a way to get rid of this I in the bottom. That's how you do division. Get rid of the I in the bottom. And to get rid of the I in the bottom, we're going to use a conjugate. Okay, so conjugate, very simple idea. If you have a complex number, all you do is change the sign of the imaginary part. So if your complex number was a plus bi, the conjugate is a minus bi. You just switch the sign that's in the middle. If it's positive, make it negative. If it's negative, make it positive. That's what that means. So we'll just try that with a few numbers. I'll give you a number, and then I'm just going to ask you what the conjugate of that number would be. So remember, just change the sign of the imaginary part. So the first number is 3 plus 2i. What do you think the conjugate would be of 3 plus 2i?
3 minus 2i.
3 minus 2i. Yep. Alright. What if we had 4 minus 5i? It'd be 4 plus 5i. So you're just changing the sign of the imaginary part. What about 3i? Negative 3i. Yep. And what about 6?
Wouldn't it just be 6? It's not imaginary.
It would be 6. You could think of it as 6 plus 0i. The conjugate is 6 minus 0i. Well, plus 0 minus 0, that doesn't matter. It stays the same. So we normally would just write 6. Okay. Any question on finding the conjugate? All right, so now what does that do? Well, I'll show you. The goal is to get rid of the I in the bottom. If you multiply the top and the bottom by the conjugate of what's in the bottom, it will get rid of the I, always. So to divide two complex numbers, you're going to multiply the top and the bottom by the conjugate of what's in the bottom. And there's the example we're gonna try. So first thing we have to do is just identify what the conjugate of the denominator is. What's the conjugate of the denominator in this case?
2 plus 3i.
2 plus 3i. So what I do, because we're going to FOIL, I just put it in parentheses. And now multiply the top and the bottom by 2 plus 3i. Now just looking at it, I can already tell you when we do the bottom, it's going to be 9 plus 13. Okay. And there's a way that I did those in my head. I didn't actually even FOIL the bottom. Because they're conjugates, there's a trick. But let's FOIL them, and you will see that it is 13. Right, so let's do the bottom first. Okay. When you do the bottom, what's 2 times 2?
4.
So that gives you 4. And then you have 2 times positive 3i and 2 times negative 3i. What happens there? They cancel each other out. So when you're multiplying conjugates, you don't have to do the outer and the inner. They always cancel each other out. So all you're left with is first and last. That's all you have to do. So we did the first. Now let's do the last. What's a negative times a positive?
Negative.
It's a negative. And what's 3i times 3i?
9i squared.
9i squared. Which that's going to be, what's I squared?
Negative 1.
So it's going to be 4 minus 9 times negative 1. So it's really going to end up being a positive. 4 plus 9 gives you, that's how I got the 13. Right, so the bottom is just going to be 13. Now let's figure out the top. Are the top numbers conjugates?
No.
No, then there is no quick way to do them. You just have to FOIL it out. Alright, so 5 times 2,
10.
that gives me 10. And then I get 5 times 3i,
15i.
so that's 15i. And what about 2 times I?
2i.
That's 2i. And then I, positive I times positive 3i. That's a 3i squared. Okay, once we combine like terms, we'll have enough space to fit that. So let's see, we got 10. What's 15i and 2i?
17i.
17i. And now 3i squared.
Negative 3.
That's going to be a negative 3. Okay, so the bottom's already done. We did that. But we can still combine some more like terms in the top. What are the like terms I can combine in the top? And what's 10 minus 3? 7. And what else is still in the top? Plus 17i. Now, we basically have our answer, but we got to make sure we write it like I said earlier. Real part plus, and then imaginary part should be separate. Let's look at our problem. Okay, the real part is 7/13. And the imaginary part is 17/13. You just write each number over 13 separate. I know we originally had the I next to the 17. You can leave it there. Or sometimes when you have a fraction, people just put the I right in the middle. That would be your final answer. Any questions on how we divided those complex numbers? Okay, so that's really it for the review of complex numbers. Now we'll try finding some roots. In general, when they ask you to find roots now, unless they say in the directions different, we're finding all roots, real and imaginary. Okay, all. Okay, so let's try to find the zeros here. Is this a problem where the exponent is high enough that I need to use synthetic division first? No. What's the exponent? It's already a 2. So we can jump to what formula right away?
Quadratic.
We can jump right to quadratic formula. If it wasn't a 2, we would use rational root theorem, hopefully find an answer, and then divide by. Okay, what's A going to be?
1.
B?
1.
C?
1.
1. All ones. Okay, so we got negative B plus or minus, what's the first thing that comes under the root?
B squared.
B squared, yep. Minus 4 times, what are the two letters that go there?
B, C.
A and C, they're all ones. And what do we divide by? 2A, which is 2. Okay, so now here's where we talked about square roots. We're going to end up with a square root a negative under the square root. And we need to fix it by taking the negative out. What do we end up with under the square root when you do 1 minus 4?
Negative 3.
Negative 3. Okay. Now the negative 1 and the 2, we can leave that. But what is the square root of negative 3? Yeah?
I to the square root of 3.
Can you say
or I minus square root, or no, I multiplied by square root of 3.
Yeah, I square root of 3.
Sorry, I butchered that.
Okay, so that's one way we can leave the answer. If they ask us to separate it into a real and imaginary part, what's the real part of that number? Negative 1 over 2. And what's the imaginary part that would be in front of the I? Yep.
Would it still be I square root 3 over 2? Or is it just square root of 3 over 2?
We usually write it as square root 3 over 2, and then they put the I next to it like that. But that's how you break that down into the real part and the imaginary part. So when you write it this way, you always put a number here, you always put a number here, and then you put the I on the end. If you're going to write it in what's called standard form. There you go. So there are your two roots. Questions on them? Yeah.
Could you just go up the equation again? Thank you.
You could use factoring if it applies. We generally don't factor with complex numbers, so that's why we did quadratic formula. But it doesn't mean every single problem now is going to come out imaginary. Some might not. This one did. All right, now let's go back here. Look at the two answers you got. Negative 1/2 plus root 3 over 2i. Negative 1/2 minus root 3 over 2i. What did I just say those two things are called? You got two answers here, and how do they compare to each other? Yep, they're conjugates. Okay. Anytime that you solve a problem, complex answers always come in pairs. you can never have an odd amount of them as a solution. They always come in pairs. So if I tell you I am thinking of a problem and 2 plus I is a root, then you automatically know 2 minus I is a root. And they always come in pairs. So that's important. You can never have an odd amount of complex answers. Never. You can have 2, 4, 6, 0. You can have 0 complex answers. But you cannot have an odd amount. So any question on that idea that complex answers always come in conjugate pairs? Yeah.
I don't really know what it's like. What does that mean when you say that?
So that means if you have a problem and you know 5 plus I is a root,
Yeah.
then 5 minus I has to be a root as well.
Oh.
They always have to come together in pairs.
Okay. Okay.
Yeah. If 2 plus 3i is a root, 2 minus 3i is a root. They come together. Okay. Any other questions on that? Okay. Let me just see. Yeah, I'm not going to do that. So I'll give people a chance. Make sure we have that copied. Alright. Think of an odd degree polynomial. Okay, for example, like a cubic. Cubic would look something like that. How come an odd degree polynomial is always going to have at least one real zero? What does an odd degree polynomial always have to cross? Yeah?
They always cross the x-axis.
Yeah, it has to cross the x-axis. And wherever you cross an x-axis, that's a real answer. Now, is that true for a parabola?
Nope.
If I draw a parabola, will it always cross the x-axis? No. That one doesn't cross. But odd ones always will. Because one side of an odd goes down, the other side goes up, and it's always connected. So odd degree always crosses the x-axis somewhere. No, but not even. Parabolas don't have to. Okay, let's try this one. Am I going to get a real answer in that problem? X cubed minus 1. What do you think?
Yeah.
Yeah, how come?
It's an odd degree polynomial.
It's an odd degree polynomial. It's a degree 3. I guarantee it's going to cross the x-axis somewhere. What we have to do is generate a list of possibilities where it could cross the x-axis. And how do we generate a list of numbers that we can then check out on the calculator? Yeah?
Rational root theorem.
Yeah, the rational root theorem, the p and the q. So now we're going to do just like we did yesterday. We're going to find the p's and q's and then see if one of them works. Kind of a hint here, one of them has to work, because if it didn't, you couldn't go any further with the problem. So, all right. What are my factors of the constant?
1 and negative 1.
1 and negative 1. And my factors of the leading coefficient?
1 and negative 1.
1 and negative 1. So when I make my list, when you take all the p's and divide by all the q's, what do you get?
1 and negative 1.
Just 1 and negative 1. Now, normally, I would type this in on the calculator and see where it looks like it crosses. But the list of numbers is so small, and the formula is simple enough that I think I can plug these numbers in for x quicker than I can graph it. If you plug in 1, what's 1 cubed?
1.
Minus 1?
0.
There you go. We just found the 0. If the formula was more complicated, or this list of numbers was a lot bigger, then I would graph it. and then just see where it crosses the x-axis. But this one will cross at 1. Is there any question how I did it without the calculator? We could check -1 as well, but we know 1 works, so let's use that. Once we know we can plug in 1 for x and get 0, what do I do with the 1?
Synthetically divide.
I do synthetic division. Yep. Put the 1 on the outside. What's going to be your coefficients on the inside?
Do you even need to bother doing synthetic division? Because like you already know that there's going to be a 0 before the 1, for the -1, and then you're going to do -1. It's going to have to go there.
Well, we know we're going to get 3 answers, right? We have to get 3 different answers.
So they're all just going to be like variations of 1.
No, the other 2 are going to be imaginary.
Okay.
Yeah.
Okay.
So the other 2, we're going to have to use quadratic formula and see what happens.
Okay.
So we know 1 is an answer, so let's divide by it. What would be my numbers on the inside?
1, 0, 0, 0, and 1.
And -1. Okay, what do we do with the 1?
Bring it down.
Bring it down. Okay, multiply 1 times 1,
1.
and then add,
1.
and then multiply,
1.
1, and one more time,
1.
1,
Uno.
0.
0.
0.
So we already knew what is the 0, that's my remainder. We already knew we were going to get 0 because we plugged it in and we checked it, and it was a root. So we can start making a list. So the roots are 1, and we still need 2 more because the highest exponent was a 3. So that's how many answers we need to get.
Now we.
What am I going to focus on here?
The quotient.
The quotient. Look at the quotient. 1, 1, 1. 1, 1, 1. We've already done the problem from here.
Oh my goodness.
So now, what you would do in this problem is what we did in example 4. You would write out x squared plus x plus 1 and use quadratic formula. So the other 2 roots are -1/2 plus or minus root 3 over 2i. So I'm just going to put C example 4. What did I just say? Was it -1/2?
Yeah, -1/2 plus or minus square root of 3 divided by 2.
Now, it's not always going to happen that you've already done a problem earlier to help you do the one you're doing now. This time it did. If you couldn't have found this one, then we would have been stuck because you wouldn't have had anything to do synthetic division with. So I will make sure that this number, I will make sure that a number from this list always works in these kinds of problems. Any question on it?
So you're saying, just to double check, right? The highest degree of the polynomial is the amount of roots it has, right?
Yes. So notice here the highest degree was a 3. We had 3 answers. Okay. When we did this one, the highest degree was a 2, and we had 2 answers. In fact, that's what I'm going to write down right now. So the total number of zeros, or the total number of roots that you get, is always equal to the degree. If you were solving a 5th degree problem, you would have 5 answers. Answers might repeat. We saw that yesterday. Okay? You can have an answer that repeats, but there still has to be 5 answers. So let's say you had a cubic. How many zeros would it have? 3. How many roots would it have? 3. When you factor it, how many factors would you have? 3. Right? You'd have 3 of everything. And that idea that you always have the same number of factors as the highest exponent, that's called the linear factorization theorem. If you have a polynomial with a degree bigger than 0, so we're not talking about constants, but anything that's linear or higher, So linear, quadratic, cubic, keep going up. You will always have as many factors as the highest exponent. So what's the highest exponent? 3. So when I factor that, how many sets of parentheses do you think I'm going to have? 3. That's how it does factor. Now, how would I figure out that it factors like that without me telling you? Well, I would have looked at all my factors of the constant, all my factors of the leading coefficient, wrote down my P's and Q's, and then used the calculator to see, is one of the P's and Q's close to where the graph crosses the x-axis? And then I'd have to do synthetic division. Right. How about if I factored something like, well, what if I had a problem and it ended up with that many factors? What would the highest exponent?
5.
Yeah, this would have come from a problem that had an x to the 5th in it. What problem would it have come from? I don't know. I'd have to FOIL all that out and see. But what I'm trying to show you on this one is this problem has 5 answers. What would you plug in here? -1. In here, there's 2 answers. And then what would you plug in here? And then here? And then here? 2. So 2, 2, 2. That's 3 answers. And -1 and -1 is 2 more answers. Even though they're repeated, that still counts as 5 answers. They're just not all distinct. So the name for that, we use the word like how many times it happens. That's called multiplicity. So -1 repeats twice. The word multiplicity is just like saying repeats. Okay, so -1 repeats 2 times. 2 repeats, I didn't write it. How many times does it repeat? 3. 3 times. We generally don't have to identify how many times an answer repeats, if it does at all. How about in this top one? Are there any repeats in those answers? No. -1, -2, +3. Question on that? So the last 2 problems we did, I gave you a polynomial, and then I asked you to factor it or use quadratic formula to find the roots. Now, let's, I'm going to switch that. I'll make sure everybody has that first. Okay. So, find a polynomial with roots. Here's going to be my roots. 3 and 2 plus I. What do you automatically know, even though they didn't write it? But I said this earlier. Yeah?
2 minus I is also a root.
2 minus I has to be a root. Has to. So how many roots am I working with? 3. So the first step to figuring out where these came from is to figure out the factors they came from. How many factors am I going to write down? 3. Okay, let's start with the first one because that's the easiest one, and then we'll apply it to the next 2. If 3 is a root, or 0, what could I put as a factor? So when I fill 3 in, it comes out to 0.
X minus 3.
X minus 3. Now let me read that a little bit kind of more general. X minus the root. That's the pattern. It's always X minus, and then write down the root. So what do you think the second one would be?
Minus 2i.
Plus I.
What's the root?
2 plus I.
The whole root is 2 plus I. That's x minus the root. Okay. And what do you think the last one would be?
X plus 2 minus I. X minus 2 minus 1.
X minus, what'd you say?
Minus 2 minus I.
X minus 2 minus I. Yeah, I just had to think that out now. Yep. So the pattern is always x minus, and then put the root in. Now, when it's just a real number, that's simple. X minus 3, there's nothing we can do with it. What do I have to do with the negative on those other two? Yeah, I have to distribute it. Okay, so let's distribute it. And what do you get if you distribute out that negative? X minus 2 minus I. And what about when you distribute the negative on this one? Yeah?
X minus 2 plus I.
Yeah. X minus 2 plus I. Now, when you write a polynomial, there shouldn't be any i's in the answer. You could have like 8x cubed plus 4x squared minus 3x plus 6. You should never have any i's in it. So somehow all these i's are going to disappear. The way they disappear is we're going to multiply these together. Right? Forget about the x minus 3 right now. Don't do anything with that one because that doesn't have any i's. Just leave it over here. But now let's multiply these two together. We're going to FOIL and watch what happens.
Why does it always default to x minus the root? Why is it never x plus the root?
That's just the pattern you always have to follow. It's always x minus the root.
Is there a reason you have to follow the pattern?
Yeah. So you'll get it right.
Got it.
I could explain for a while, but it's just not worth your time. It'll take like 10 minutes to explain it. But I mean, well, think about like right here, right? If you plug 3 in for x, what's 3 minus 3?
0.
0. All right, let's try x plus the root instead. Let's see if that works. If you plug 3 in here, do you get 0 now?
No.
You get 6. So no, you got to do x minus the root. Does that make sense?
What if you had like negative 3 is the root?
If negative 3 was the root, then x minus the root is still how you do it, because then it would be negative 3 minus negative 3, which is 0.
Yep. Okay.
If you put a plus here, it doesn't work. You don't get 0. That's the simple reason. Okay, so now let's distribute this out. All right, one step at a time. What's x times x? X squared. What's x times negative 2? Negative 2x. And what's x times I?
XI.
Yeah, we just write xi. And I told you, everything with an I is going to disappear. So keep going and watch what happens. What's negative 2 times x? Negative 2x. What's negative 2 times negative 2? 4. That gives me a 4. And what's negative 2 times I? Negative 2i. Right? And now let's do it one more time with the negative I. What's negative I times x?
Negative I.
Negative ix, or negative xi. Same thing. So we just got a negative xi. What's negative I times negative 2? Yep, plus 2i. And what's negative I times positive I?
Negative I squared.
Negative I squared. And I squared is what number?
Negative 1.
So negative I squared really means negative negative 1 plus 1. Okay, so I did it in different colors so you can see what I distributed for each part. The x goes to all 3, the negative 2 goes to all 3, and then the negative I went to all 3. Is there anything in there that cancels out? All right, like which ones? Positive xi, negative xi, yep. Positive 2i, negative 2i. So half of that just disappeared. Okay, so let's see what we have left. Is there anything I can combine x squared with? Nope. How about negative 2x? Another negative 2x, which is? Okay, so we got that, we got that, we got that. Anything else?
4.
Yep, 4 plus 1 is plus 5. Okay, now we're on the last step. Any question how we got to that? Okay, what do you think the last thing you have to do is? Yep, distribute it one more time. This one's going to be a little shorter because instead of 3 things distributed to 3 things, this is 2 things to 3 things. So it's going to be 6 instead of 9 that you add up. Okay. What's x times x squared? X cubed. What's x times negative 4x?
Plus negative 34x squared.
What's x times 5? 5x. What's negative 3 times x squared? Negative 3x squared. Negative 3 times negative 4x. 12x. Negative 3 times negative 4x. And what's negative 3 times 5? Negative 15. Okay, do I have any like terms there? Okay, let's start with x cubed. Anything there?
No.
No. Let's go to the x squared. Anything there?
Negative 3x squared and negative 4x squared.
Yeah. What's a negative 3 and a negative 4 together? Negative 7. We got that, we got that, we got that. How about 5x? 12x. So that's 17x. Anything I can combine with the negative 15? Nope. So there's the polynomial that would have those 3 answers as roots. Now if you graph it, which one of these roots would you see on the calculator? Yeah, it would cross the x-axis at 3, and that's the only one you'd see. Question on that? All right. So let me double check something for you.
Oh, look at that. Yeah, use that eraser, boy. Use that eraser. I told you that. Oh yeah, use it again. Use it again.
Huh?
No, not him. Not me, not you, him.
Oh.
Yeah, he's telling me to erase more problem.
And I think, yeah, that's good. All right, so what I'll do is I'm going to pause it, and then I will add the list of topics that will be on the test. Actually, I think I already have it written. I'll just copy and paste it. I'll put that in real quick.
I'll do it.